So we talked about for the last few days, 3 days to be exact. We talked about chemical kinetics, right? And chemical kinetics is leading up to us to doing all these things that have to do with what we call equilibrium. Okay, and so I'm talking about solution equilibrium, chemical equilibrium, acid-base equilibrium, right? All these things that have to do with equilibrium. And the reason why is because up until now, you've always been taught that a reaction goes to completion, right? You have like sodium and you have chloride, you put it together and it makes salt, and all that sodium and all that chloride becomes salt, right? That's what you've been told. Well, we've been lying to you. That's not true, actually. We don't actually have reactions that go to, very rare do you have a reaction that goes complete all the way to completion, right? And so the basis of the next few chapters is describing to you all the situations, which is most of them, where you don't have 100% conversion of the reactants to the products. Okay, so we call that chemical equilibrium. Okay, we call that chemical equilibrium. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. In a figure above, the equilibrium is finally reached in the third picture. So what you see here in this picture, right, is a sample of very cold dinitrogen tetroxide, right? Dinitrogen tetroxide. And when it's inside this, when it's very cold right here, right, it's a colorless gas. But as the gas starts to warm up, it starts to convert into nitrogen dioxide, right? Nitrogen dioxide. Okay, and most of the time, and up until now, you've been taught that this conversion happens, right? This reaction happens where di, uh, dinitrogen tetroxide going to nitrogen dioxide is going to go 100%, right? Where you won't have any more of the reactant and you only have products left over, right? But in reality, that's not true. In reality, this reaction will proceed until what we call the equilibrium point is, right? And it's the equilibrium point will have a mixture of both reactants and the products, right? Here we have nitrogen dioxide and dinitrogen tetroxide all mixed together, right? And that's called the equilibrium point. And specifically, the equilibrium point is the point where the rate of reaction, right? And this is why we had to learn about kinetics last week, right? It's specifically when the rate of reaction for reactants turning into products is the same thing as the rate of reaction for the products turning back into reactants. Yes, that is crazy, but it's true, right? Your products, even though you've made products from those reactants already, those reactions are actually reversible. They can go backwards and become reactants again, right? Depending on the conditions. Okay. So this is the biggest thing I want you to know from this equation, or not this equation, but this definition right here. What is chemical equilibrium? It's the point at which the reverse reaction and the forward reaction turn in are the same rate. They're exactly the same rate. And so what that looks like in reality, in real life, is that you'll always have this. You'll get to a point where the concentration, right? If it's a gas, it would be pressure, but if it's a solution, it'd be concentration. The concentration of the reactants will remain constant, and the concentration of the products will remain constant after the equilibrium point, right? Nothing will change. And the reason why that is because the rate of creating the products is the same as the rate of creating the reactants, right? So there won't be any change in the number of moles of products or reactants once you reach equilibrium. Make sense? Right? So let's look at that graphically here. Um, there we go. I was like, why is it not moving? Okay, let's look at it graphically here, right? So this is the graphical representation of what we saw up there in the pictures, okay? And we have nitrogen dioxide, right? And its concentration is going up. And here we have dinitrogen tetroxide, and its concentration is going down, right? And so the reactions are happening, right? And we're making tons of product, right? And then we're losing concentration of the reactants, right? And you just keep on going, and then you get to this point, right, where the concentration of both reactant and the product, right, the reactant and the product stays the same, right? And that's called the equilibrium point, right? That's called the equilibrium point. Okay. There's there's no more nitrogen dioxide being made than there is dinitrogen tetroxide being made, right? And so the concentrations remain constant after the equilibrium point. So if we then look at that based on the rate, right? The rate of making nitrogen dioxide here is steadily increasing, steadily increasing. It's going up pretty fast, right? Whereas the rate at making the or destroying, not destroying, I guess it would be decomposing the dinitrogen tetroxide is going down, right? It's going down, but they go up and go down to a point in which they meet each other, and now the rate is the same. And the rate is the same after what? The equilibrium point, right? Does that make sense so far? Not too crazy, right? Okay. So just remember, a system approaches equilibrium. Both forward and reverse reactions are occurring, okay? Right? So the forward and reverse actions are occurring, right? The forward reaction here, reverse reaction there, they're going towards each other, right? At equilibrium, the forward reaction and reverse reactions proceed at the same rate, right? Which is this point right here. And then once equilibrium is achieved, the amount of each reactant and the amount of each product remains constant, right? And so here's the concentration there and the concentration there of both reactant and product, and it remains constant after equilibrium. Okay, it's basically everything I said on the first slide. Okay, it's everything I said on the first slide. So the thing I want you to notice here is that we have two new K things now, right? Remember what K stands for? Exactly, it stands for the rate constant. Thank you, Mary. It stands for the rate constant, right? And here we have Kf, right? Kf and Kf. So Kf is the rate constant for the forward reaction, okay? The rate constant for the forward reaction. There's also another one called Kr. What do you think that means? Close. It's the rate constant of the reverse reaction, right? So Kf is the rate constant of the forward reaction, and then Kr is the rate constant for the reverse reaction, okay? So your very first question today is this: which of the following is true about chemical equilibrium? Which of the following is true about chemical equilibrium? Dan, you got it right on time for the first question. You do have pants, right? Because we have lab today. It's practical. Yeah, it's practical. So you'll be in there actually in the lab doing stuff. Don't worry, you got 15 minutes after class to go run and get some pants. Well, everybody needs a new pair of, Texas Wesleyan pants. That's not that bad. That's not that bad. I know, like Auburn pants are 70, 80, almost 100. Because they charge an arm and leg for the licensing. All right. We've only got 4 responses so far. How many people do we have here today? I thought Oshana came in just a second ago. Did she leave? I mean, her stuff is here. I think she left. So 10. Wait. Wow. All 12 of you are here today. That's crazy. All 12 are here today. Okay, so we should get 11 responses since Oceana's not here. Which of the following is true about equilibrium? Oceana, do this real quick so I can get you on the rolls, on the attendance. Read it carefully, though. Which of the following is true about equilibrium? Which of the following is true about equilibrium? Did you scan it? Okay, good. Which of the following is true about equilibrium? You didn't see any part of me talking about that, so I don't know if you'll be able to answer that question because that was the last slide, the one while you were gone. Wow, you got it right. All right, the vast majority of you got that question correct. The answer is indeed D, all of the above. Those are all true of chemical equilibrium, right? Those are all true of chemical equilibrium. I'm actually very impressed with Oceana because she missed the entire part I was talking about with it, and you got it right. Yep, that's true. So, but that's true. Technically, you're all right, but you're not all completely right. So people who answered D were completely right, right? So good job there, right? Because in fact, remember these rules about equilibrium, okay? A system at least as a system approaches equilibrium, both the forward and reverse reactions are occurring. That is correct. At equilibrium, the forward reverse reaction at equilibrium, the forward and reverse reactions are proceeding at the same rate, and then that's true too. And once equilibrium is achieved, the amount of reactant and product remains constant. Okay, those are three of the most important parts of this chapter. Okay, you need to remember that. It will help you answer a lot of questions. Okay, so let's talk about then a system in dynamic equilibrium. Okay, products are being made, but reactants are also being made too at the same rate, right? In dynamic equilibrium, which we just said that. We just said that. The total amount of product and the total amount of reactant never changes. It never changes. Okay? It never changes. Because if you think about it, if you have a reaction, right, and you have it in like a closed system, right, inside of a little container, and you're doing this reaction, matter can't be destroyed or created, correct? Right? So once you put those reactants in there and it starts making the reaction, unless you add more stuff to it, the total number of reactants and products will always be what? The same, right? Will always be what? The same. So neither reactant nor product can escape the system, which I just said that because you have a closed system. Okay, you have a closed system. And then the ratio of the concentration always stays constant, right, after equilibrium. Always stays constant after equilibrium. So when we look at equations now, you'll never see them where you just have one arrow. Now they have two arrows, right? You can go the forward reaction, right, where you go with the dinitrogen tetroxide becoming the nitrogen dioxide, right? But you can also go backwards, the reverse reaction, right? So from now on, your reactions will all have double arrows, unless you're only talking about one part, one half of it, right? The forward reaction and the reverse reaction. But in general, they'll be like this now, okay, with a double arrow. And since a system at equilibrium, in a system where both the forward and reverse reactions are being carried out, we write the equation with a double arrow now. So remember that, okay? I'll have word problems, for example, where you have to write out the equation. And if you forget that double arrow, you will lose points for that because it's very important to remember that we are now in the point in your chemistry careers, right, where reverse reactions can happen, okay? It's no longer just going one direction anymore. So let's take a closer look at the reaction that is the decomposition of nitrogen tetroxide gas into nitrogen dioxide gas, right? So you remember this already from the last chapter. We've got the rate, right? But instead of it just being the rate constant, but like before, because before it was just the rate constant, and they were all going to the forward reaction and everything was becoming products, right? Now it's the rate constant with an F on it, which I said before means what? It's just the rate constant of the forward reaction, right? And it looks exactly like it does in the chemical kinetics section, right? It looks exactly like it does in the chemical kinetics section, right? Okay. And so the reverse reaction, though, right? The reverse reaction right here is going to be the NO2 gas becoming the dinitrogen tetroxide gas, right? And you can see here the rate law is Kr instead of Kf for the reverse reaction, right? And just like in the chemical kinetics section, we use the coefficients right? To figure out figure out what our exponents are, right? And since this is the rate equation for the reverse reaction, right? This is the rate equation for the reverse reaction, and it's got an exponent of 2, right? That means what? Yes, second order. Thank you. Thank you. Yes, it means second order. All right. So let's take a closer look here then, right? We then learned just a second ago, though, right? When you reach the point of equilibrium, the rate of the forward reaction is what? Equal to the rate of the reverse reaction, right? That's why there's no more products being made, and that's why there's no more, or let's say there's no more net products being made, and no more net reactants being made, right? So now we know that rate at equilibrium, the rate F, or rate forward, is equal to the rate reverse, okay? And then so that means then we can do this, where we say the rate constant, the rate law of the forward reaction is equal to the rate constant of what? I mean the rate law of the what? The reverse reaction. Okay? But that's only true when? After equilibrium, right? It's only true after equilibrium. Okay? Like I was saying before, we've crossed that point now where it's going to be a lot of math, right? The rest of the semester is going to be mostly math. Okay? So be prepared for that. The first half was conceptual stuff, right? But the second half is going to be mostly math stuff. Math and chemistry, right? So we can do this thing now where we do the ratio of the reverse reaction, right? Or the products, right? Basically the products, the ratio of the products divided by, not the ratio of the products, the concentration of the products divided by the concentration of the reactants, right? With the exponent of 2 there because of the stoichiometry, the coefficient that was 2, right? And now we have a ratio of products over what? Reactants, right? Which is equal to the forward reaction constant divided uh, by the reverse reaction constant, right? And that alone in itself is called a constant. Specifically, it's called KEQ, which is called the equilibrium constant, right? The constant we get, the rate constant we get when we're at equilibrium is called the equilibrium constant, okay? It's called the equilibrium constant. So the biggest thing about this, right, the thing that I want everybody to remember is when you're writing out these rate laws for equilibriums, right, and the equilibrium constants, the products will always be above the reactants. Okay, remember that. The products will always be above the reactants. Okay? And then the exponents will always be based on what? The coefficients from the balanced chemical equations. Okay? Those are two important things to remember about writing rate equations. Because you'll see, right, just like we did in chemical kinetics, if you can't write the correct, there we go. If you can't write the correct rate equation, you're not going to be able to solve the problem, right? You won't be able to solve the problem. Okay? All right, next question. Which of the following is true about a system in dynamic equilibrium? Okay, which of the following is true about a system that's in dynamic equilibrium? I really hated math when I was going through school. I was like the worst person at math. But math became more fun when they applied chemistry to it for me. Because otherwise, it's just like, just have numbers, just piddling around with numbers, right? But now I actually have things I can see in my hands and take out on the shelf and put it into things and make things happen with, right? Math is so theoretical, right? But when you apply math to chemistry, you can actually do experiments. You can actually make something happen, okay? All right, which of the following is true about a system in dynamic equilibrium? The products are being made, but the reactants are not being made. Total amount of reactants and products doesn't change. Only the reactant can escape the system, or the ratio of the concentrations is variable. Still waiting on two people. One more person. One more person. One more. One more. Awesome. Awesome. All right. So this is the distribution, the breakdown, right? The vast majority of you got that one correct once again. B is the correct answer. Let's look at why B is the correct answer. Okay? It's not why B is the correct answer. And watch it not be B. I'm kidding. I'm pretty sure it is B. Right? Okay, the first one says products are being made, but reactants are not being made. Why is that false? Exactly. Reactants are being made during the reaction equilibrium. Only the reactant can escape the system. Why is that not false? Why is that false, rather? Right. Nothing can really escape from the system unless you have the system open, and then both things can escape. Right? It's not one or the other. Right? Makes sense? And then this one here, why is this one not true? The ratio of the concentration terms is variable. It's constant, and it's not variable, right? So the only one here, the only answer correct here is the total amount of reactants does not change. Product and reactant does not change. Okay? So we introduced this a little while back, the Haber process, right, where we were making like ammonia for like fertilizer. I think I can't remember exactly what the example I used was, like so long ago. Seems like the first day of the semester was so long ago, and we've covered so much stuff. And I'm sure you have all that in your head right now, right, for the final exam, right? It's gonna be great. Okay. So in the Haber process, we have ammonia, right? And ammonia combines with hydrogen gas, right? I'm sorry, let me say that one more time. Nitrogen gas combines with hydrogen gas, and it becomes ammonia gas, right? And that's called the Haber process. So in this very simple equation right here, we can show you that the equilibrium constant here, right? So Kc stands for equilibrium constant, okay? And specifically, it's the equilibrium constant that's based on concentrations. That's why it's a C, okay? The equilibrium constant depends on the stoichiometry. So just like I said in the last slide, right? The products here, which is ammonia, right? It's always over what? The reactants, correct? Right? And then the exponents that we see on the different concentration units on the different species here, right? Like for the ammonia here, the 2 exponent comes from where? The coefficient that's in front of the 2, right? And then the 3 comes from the 3 that's in front of the coefficient in front of the hydrogen, right? And what's the coefficient for the nitrogen gas? 1, exactly, because the coefficient in front of nitrogen is what? 1, okay? That's the first step to getting a KEQ equation correct, right? When you're trying to do an equilibrium problem, like an equilibrium word problem that I might give you on an exam or assignment or a quiz, right? That will be the first step to getting that thing right, is by having the right equation to use. Okay? So let's take a look at this then. This reversible reaction called the Haber process. What do you start with to reach equilibrium, right? So here, this is going to be the same thing that we saw before with the dinitrogen tetroxide decomposing into the nitrogen dioxide, right? It's going to be the same thing before, but the only difference now is that before you had a decomposition reaction, correct? Now you have a combination reaction, okay? You have a combination reaction. So here again, right, we have concentration, right? We have concentration, and we have then time, of course, right? And if we start with only reactants, right, just this side, that means we take nitrogen gas and we take hydrogen gas and put them together, right? Just those two things. This is what it looks like, right? We have our equilibrium point here. We know that it's our equilibrium point because the concentrations are constant afterwards, right? But notice that As time goes by, the concentration of hydrogen goes down, which makes sense because the hydrogen is doing what? It's getting used up by being combined with the nitrogen gas, right? And so that concentration is going down too, right? It goes down to the point where it reaches a constant concentration, right? And at the same time, ammonia is being made, and the concentration of ammonia is going up, right? All the way to the point where the concentration of ammonia is constant, right? So when all three, the ammonia, the hydrogen gas, and the nitrogen gas, right? When all three reach the point where we have the same concentrations of both, right? We're at the equilibrium point. I mean, both. There's three things there. The same concentration as all three things, right? It's you get the both. You get the equilibrium. So let's do it the other way now. Let's do the reverse reaction. Okay. Here, the reverse reaction is actually going to be ammonia decomposing, right? Ammonia is decomposing to become what? Nitrogen and hydrogen, exactly, right? And so look at this thing here, right? Now we have ammonia's concentration going down, right? But then concentration of hydrogen gas and nitrogen gas is going up. And then at some point, they all reach constant concentration. And that point is what? The equilibrium. But the thing I want you to see about this is that even when you're doing the reverse reaction or the forward reaction, right? Look at this. The concentrations are the same, right? They take different paths to get there, right? One is a breakdown and one is a combination, but in the end, right, the equilibrium concentrations for this reaction are identical, right? The concentrate, I mean, there are no numbers there, but we put the graphs right next to each other so you could see that this was at the same line for hydrogen, right? The ammonia was at the same line right there, right? The orange line, and then nitrogen was at the same line all the way across. So it doesn't matter if you're using the reverse reaction or you're using the forward reaction, okay? It doesn't matter if you're using the forward reaction or the reverse reaction. You'll always end up having the same concentrations that are constant after the equilibrium point. Make sense? Right? Cool stuff, man. Cool stuff. So cool. It's so exciting. All right. So let's just talk about now, I alluded to this before, and this, alluded to how to write an equilibrium constant, okay? How to write an equilibrium constant. So this is the same thing we had before, right? When we had the kinetics problems or the rate law, right? Where little a is the coefficient for big A, little b is the coefficient for big B, little b is the coefficient for big B, right? We have the reversible arrows here because it's, it can go backwards and forwards now. And then, excuse me, little d is the concentration, is the coefficient for big D, and little e is the coefficient for big E. How's that actually a little bit different from the kinetics one? Remember what the kinetics one had in it? Say again? Exactly. Instead of being DE, it had CD. Why do you think they changed it for this? So you don't get confused with KC, right? The little KC right there. Does that make sense? Right? There's already a C in this because it's the equilibrium constant. So constant stands for the C this time. That's why they changed it, right? So you don't get confused. And now the products are D and E instead of C and D. Make sense? So don't get confused that you have like a chemical kinetics problem, right? And you have to do the rate law and have C's in there, right? But then you go over to do a equilibrium problem and you don't have any D's and C's at all, and it's all D's and E's, right? Don't get confused. Make sure you know what kind of problem you're doing, okay? So the equilibrium expression, this entire thing is called the equilibrium expression, right? And it's just like it would be on the chemical kinetics one, right? Where the equilibrium constant is equal to, remember I said this before, and I mean, it's going to be said 5, 6 more times today. It's always going to be the products over what? The reactants, right? And then the little letters, the lowercase letters, which are the coefficients, will act as the exponents for each of the concentrations, right, of the reactants and products. Okay. So interestingly enough, when you're doing this with just regular old solution, right, where you have like, you have like a two solids that you dissolve into liquids and you mix them together and a reaction occurs, that's the kind of thing you would use, right? But if you're mixing two gases together, it's actually written this way, right? Where now the equilibrium constant, right, is actually Kp because that stands for pressure. P stands for pressure, right? Because you can use the pressure of a gas as analogous to, right, the concentration of a solution. Does that make sense? The pressure of a gas is analogous to the concentration of a solution, okay? And so what happens then is that Kp is literally the same thing as this up here. It's still reactants, sorry, products divided by reactants, but instead of doing the big letters D and E, A and B, now it's the partial pressure of D, right, times the partial pressure of E divided by the partial pressure of A times the partial pressure of B, right? And then the lowercase letters still being the exponents, right, from the coefficients. So just remember, right? And some people go back and forth and they use them interchangeably, right? But just remember, if you have a Kp, that's going to be based on pressure. If you have a Kc, that's going to be based on concentration, right? And concentration is always in solution. And then Kp is always going to be two gases, right? Gases mixing together and becoming something else. Okay? I know, a lot of rules, but you'll get it. I mean, I got it, and I'm a dumbass. Excuse me, I'm stupid. So, I mean, I get it. I'm gonna have to cut that out, aren't I? Anyway, next question here. What is the equilibrium constant dependent on? What is the equilibrium constant dependent on? This next few stretches here for you guys will be very difficult, and I know it will be because it was very difficult for me when I was going through Gen Chem, but I got through it, and you will too. And I'm all the better for it because now, I'm a chemistry professor. So just think a dumb guy like me was able to get it. You guys can get it. Okay, so we're going to do equilibrium constant now. Got 8 responses, 11 responses, one more response, waiting for that one more response, still waiting for that one more response, still waiting for that one more response. There we go. There it goes. Okay, so let's take a look at this here. It's about half and half. Half the people, more than a little bit more than a majority of the people did get the question correct. The answer is in fact B, but the others picked all three kinds of different things there, right? And this question is in fact B because remember, right? Stoichiometry means the same thing as what? Coefficients, right? It means the same thing as coefficients in front of the equations, right? And when you're writing out the equilibrium equation, right, or the equilibrium expression, right, it really much depends on the coefficients, right, the stoichiometry, right? Otherwise, you wouldn't know what to put there in those exponents, okay? Make sense? I believe there's actually a line in there. See, there it goes. The relative amount of change is based on stoichiometry, right? I knew I wrote it in there somewhere. So that way, when you're going through the notes, you can actually see that it says that there, right? Okay, so let's keep talking about gases and equilibrium, right? It's a little bit more different, a little bit more difficult, rather, to do gas equilibrium because you've got to take into account the properties of gases, right? So we can compare the equilibrium constants based on concentration to one based on pressure, right? So the thing about it is that for gases, you're going to have to use the ideal gas law, which is PV equals nRT, okay? PV equals nRT. Which I told Mary yesterday when she was getting help, and she's like, "What? The ideal gas law? What's that?" What's R? It's the ideal gas constant, right? So that means there's going to be a question on your assignment that requires that, right? And so uh, for the gases, right? For the gases, you have to use PV equals RT, where P is the volume. P is the pressure, V is the volume, N is the number of moles in something. R is the ideal gas constant, right? The ideal gas constant. So a mistake people do a lot when they do the ideal gas constant is they use the wrong units. You need to be able to look at your question and see what units it's asking for and use the correct version of the ideal gas constant, right? That has the right units. Okay. Uh, I lost my train of thought. Okay, and then T here is big T. So what does that mean? Huh? What does T mean when it's a big T? Temperature, yes, not time, temperature. Okay, little t is time, big T is temperature. Okay, so for the most part, I'm pretty sure most of the time when you're doing this equation, the version of the ideal gas constant that you're going to be using for R is the 8.134, I believe. 8.134. Okay, I'm pretty sure that's right. But it also depends, like, again, it's going to depend on what the question's asking you for. Okay, there's multiple versions of the ideal gas constant with uh, there's multiple versions of the ideal gas constant. Should be. Did I say that wrong? I don't usually have the constants memorized. So, Mary, what was it that you used yesterday? Do you know? Okay, listen. Maybe I don't know who's right here, so I'm gonna make sure. You're probably right, but let me make sure. Let me Google it real quick because I don't have the gas constant memorized. Ideal gas constant. You're crazy, Mary. It is. It's 8.314. Yes, the one that you should be using the most of, right? The one that you should be using the most of is the ideal gas constant that ends with 8 point, not ends with, is 8.314, right? And the reason why is because that the unit for that one is joules, moles, Kelvin, right? The other ones have the wrong units, okay? So make sure that you're using the correct one, 8.314, when they're asking for the ideal gas constant, okay? Say, you'll get problems. You'll have a word problem where you'll have to use this equation, and there's multiple versions of the ideal gas constant based on their units, right? But for this equation right here, for doing it with gas equilibrium, the ideal gas constant that you need to use is 8.314. 314. That's okay. I'm just calculate too, right? You're so close, Mary. You're so close. So close. No, that's exactly what you said. I mean, you could if it was a multiple choice question, and you probably get the answer pretty close, right? But I could be super sneaky and do that too, and put that answer in as a choice. Or it might be It might be one of those open ended questions where you start out with the top and then have like five questions linked to it. Huh? I wouldn't do that to you. I wouldn't do that to you. What class is that? Here? Oh, I wouldn't do that here. Well, it depends because part of organic chemistry is having memorized reactions, right? And so if you have them memorized, it's pretty easy. Huh? Anyway, back to this, okay? We're not talking about organic. You have to make it through here first before you get to organic, okay? I mean, I can always help you with organic too. I want to teach organic chemistry. Anyway, so the ideal gas law, just remember you're going to use R. Usually something else will be given to you, like you'll get pressure, volume, temperature and you have to find the number of moles, or you'll give like you'll or something like that. But the thing that you're going to say is, oh, but you didn't give me what R was. Well, R is always going to be 8.314. Okay. So for these problems, for the problems that deal with this, and so you got to rearrange a few things here though to make it look like an equilibrium constant, right? Because the chapter in gases is over. We did that in Chem 1, right? So you got to be able to apply the ideal gas law now to chemical equilibrium. And the way we do that is by seeing that when we rearrange things, we can divide both sides by V, right? And then you'll get pressure, okay? And then you'll get uh, the top part, nRT, divided by V, right? And so when you do that, you get N divided by V. And what does that look like to you? What does N divided by V look like to you? It's how you figure out the concentration of something, the number of moles divided by the liters, right? Number of moles divided by liters. So that's how you figure out the concentration of something. It literally says it right here, see? N divided by V is what? Concentration, right? It's concentration. Remember when you have these square brackets, they're concentration. So knowing all that now, okay, we can say that the equilibrium constant for pressure is equal to the regular equilibrium constant using concentration multiplied by what? The ideal gas constant and the temperature to the change in the number of moles. Okay, to the change in the number of moles. And what is the change in the number of moles? Is exactly what it sounds like. It's the number of moles of the gas product minus the number of moles of the gas reactant, right? Because when a reaction is occurring, you're losing one, right? And you're getting more of the other. So there's a change in the number of gas moles of something, right? And that's what the change in N is. That's a change in number of moles. That's number of moles of gas product minus the number of moles of gas reactant. Okay? That's good stuff. It's absolutely good stuff. It's a good time. So let's look at this now. This is it demonstrated right here, right? This is the last slide demonstrated. Okay? As you can see here, the ratio of nitrogen dioxide to the concentration of nitrogen dioxide squared to the concentration of dinitrogen tetroxide remains at a constant temperature, remains constant at this temperature, no matter what the initial concentrations of nitrogen dioxide and the dinitrogen tetroxide are, right? Because it's a reversible reaction, right? In experiment 4, right here, we started out where we had no NO2 and we were getting more NO2, right? But over here, we're starting out with with mostly NO2, right? And no N2O4, right? And so it doesn't even matter that one side one experiment we start with more NO2, and the other experiment we start with more N2O4, right? In the end, when you get done with the reaction, you always end up having what? Equilibrium, where the rates are the same and the concentrations remain constant, right? Does that make sense? Okay. So the takeaway message from this is that the equilibrium constant in these gases, right, is constant in these gases, right, remains constant and goes like the same thing regardless of the starting concentration. Okay, does that make sense? Regardless of the starting concentration. Okay. So let's take a look at this with using experimental data. Okay, let's look at this using experimental data here, okay? Again, we have the initial and equilibrium constants of the nitrogen gas, dinitrogen tetroxide gas, and the nitrogen dioxide gas at 100 degrees Celsius, okay? So here in the first two experiments, or first three experiments, we've got no initial concentration right there, right? It's actually 0 of the N2O4, okay? N2O4. And as we go through here, we see that for all three of these, the initial concentration, right? The initial concentration of the NO2, though, is actually increasing here, right? We have 2, we have 3, and 4 here, right? 0.02 molar, 0.03 molar, 0.04 molar, right? And then when you jump over here, the reactant is still, I'm not the reactant, sorry. The equilibrium constant is still the same, right? Pretty much experimentally, right? I mean, this little point zero zero two difference here could be experimental error, right? It could be a slight difference in the measurement of the actual pressures of this stuff or the concentrations of this stuff. But you notice that their equilibrium constant stays the same, regardless of what? The starting concentration of NO2, right? Over here, though, we start out with 0.02 concentration of the N2O4 and none of the NO2, right? And again, the equilibrium constant is still the same, right? Pretty much on the same order of magnitude, same level. Notice though that in the middle here we have the individual equilibrium constants for each of the forward and reverse reactions, right? This one's for NO2, and this one's for this one's for N2O4, and this one's for NO2, right? They actually are different, right? They actually are different. But in the end, once you figure out the KEQ, right, or the equilibrium constant of the entire system, which is when you have the products over the reactants, right? The ratio of the products over the reactants, you get the same equilibrium constant for all different reactions, all four of those reactions, right? So regardless of what the starting concentration is of the reactants, you will always end up with what? A constant equilibrium constant. That's why they call it an equilibrium constant, right? Or KEQ. Okay? Good stuff. So here's something you should remember, okay? Here's something you should remember, and it's kind of like touching our toes just a tiny bit into the water here of Le Chatelier's principle. My old boss used to say, "Stop dangling your feet in water, just jump into the pool." And what that means is get committed, right? Go all in. Stop just testing things out, right? Well, we're not going to do that just yet with Le Chatelier's principle. We're just going to dangle our feet for just a second. We'll talk more about Le Chatelier's principle next week, right? But when you have a K, right, a constant, equilibrium constant, right, that's greater, that's less than 1, right? Wait. That is the greater sign. There we go. Okay, if you have a equilibrium constant that's greater than 1, the reaction favors the products, right? The products will predominate the equilibrium. If you have one that's less than 1, right, then the reaction favors the reactants, right? And so that predominates the equilibrium. So we can see that here. I don't know why, but I was seeing those alligators like backwards just a second ago. It's really weird. When I was in elementary school and they taught me less than and greater than symbols, it was like alligators and the alligator wants to eat the bigger number type of thing. So, and then there was two of them there, and I'm like, wait a second, are they backwards? I'm confused. Anyway, the point is, this picture here, right, demonstrates that. So here we have a K that's greater than 1, and so the equilibrium lies to the right, where you're getting mostly products. If the equilibrium is less than 1, for some reason I knew that was going to happen. That's why I paused. I had this feeling that some alarm was going to go off. Oh, is that why? It's 1 o'clock? That's probably why. It's my internal clock, right? That's what it was. And then so if the K is less than 1, then the reaction lays to the left, right? So it is very probable that I will give you a question in which I give you some Ks, and you need to tell me whether or not it's going to be mostly reactants or mostly products in that reaction. Okay? Just remember, greater than 1, mostly products. Still equilibrium, but still mostly products. Less than 1, mostly reactants. Okay? Remember that. Oh, dang, I just asked you the question that I said I was going to ask you. When a K is less than 1, the reaction is what? I'm gonna go about 5 more slides, and then we'll stop, and then I'll answer some questions. Huh? No, there shouldn't be. Maybe I wrote the question wrong. Let me read it again. Yeah, I'm sorry. I wrote the question wrong. Because less than one should be favoring reactants. And it also means that reactants are predominant. Good job, guys. That was a test on you. Good job, guys. That's what happens when I write a. Maybe. We'll see. We'll see. Let's see how everybody answered first, though. Hold on. Let me just see. Hopefully, most everybody answered one or the other. Yes, most everybody answered one or the other. Okay, that's good. It's very smart. Because, well, that's the thing. Like, I might not come down on you about it, right? But if Ms. Dickens comes in and sees that your ankles are showing, she might come down on you. Yeah. Those are nice pants, though. All right. We still have 5 slides to get through. Let's get through these slides, okay? All right. So, the direction of chemical equation and the chemical equation in K, right? The direction of the chemical equation in K. The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction, right? So, if you take a gander at this up here, right, we see the, again, forward and reverse reactions, right? But one is actually the forward reaction, which is the N2O4 becoming the NO2, right? NO2, right. And then you also have this one here, which is the reverse reaction, which is the NO2 becoming the N2O4, right? Even though this is the forward reaction and this is the reverse reaction, they are both still reversible, right? They can still go both backwards and forwards. Okay? So, but just be able to identify the fact that these are both, this is the forward reaction from the previous example, and this is the reverse reaction. And so what happens here is that when you put the N over, sorry, when you put the reactants over products here, right, which is reactants over products, the products over reactants here, right, you end up with an equilibrium constant of 0.214, right? But when you put the reactants, the products of reactants here, right, then you get an equilibrium constant of 472, right, at 100 degrees. So the thing to know about this here is that the reverse reaction is the reciprocal equilibrium constant of the forward reaction. Okay, it's always the reciprocal. Okay, it's the reciprocal. So if I tell you to, if I have an equation for you, a chemical equation for you, and I want you to break it up into the forward and reverse reactions, right? I want you to tell me the equilibrium constant for each one. And the one for the reverse reaction should always be what? The reciprocal of the forward reaction. Okay? Which, if you just think to yourself in your mind, it's always products over reactants, you'll always get it right. Okay? So, let's find the new equilibrium constant of each reaction when the reaction is multiplied by a multiplier. So, what you can do actually is you can figure out a new equilibrium constant, right, by adding more stuff, right? By adding more stuff. So here we have the same reaction, N2O4 gas becoming 2 moles of NO2 gas, right? And what we've done here is that we've doubled the number of moles of N2O4, right? And it becomes 4 moles now of NO2 gas, right? So interestingly here, right, here's the equilibrium constant, right, for the normal one. Here's the one with double the concentration here, right? But notice that the KEQ for the normal is still present there, right? But now, so how do you get rid of exponents in fractions? Just a quick little, algebra review. Well, how do you get rid of those exponents, right? So when you have an exponent at the top and an exponent at the bottom, all you have to do is subtract them. And that's how you get the final number exponent, right? See, that's a good thing I told you. That's one of those things you got to remember, right? Because it's basic algebra, okay? So here we have our equilibrium constant, right? Our equilibrium constant, that's normal, right? 1 mole at 0.212. But when you double the reactants, what happens to the equilibrium constant? It gets squared, right? It gets squared. Crazy stuff. All right. So let's take a look at another one, okay? Let's take a look at another thing here. So you can actually do equilibrium constants where there's more than one equilibrium, right? Say it's a two-step problem, right? A two-step uh, uh, um, two-step reaction. Say it's a two-step reaction, right? So here is the overall general reaction right here. Okay, that's the overall general reaction. Okay, the first step of the reaction is this part where NOBr becomes NO and Br2, and its equilibrium constant here is 0.014, right? And then after that, you can take a Br2 and add it to chlorine, right, to get yourself BrCl, okay? And its equilibrium constant is 7.2, okay, 7.2. So how do you figure out then what the equilibrium constant is for both reactions when it's a two-stepper like that? All you do is you multiply the first one times the second one, and you get the third one, right? And the third one, or the overall one, is 0.1. Make sense? So if you have a multi-step reaction, you can figure out the equilibrium constant for each step, right? It's always products over reactants again, right? So it's products over reactants again. So let me just write it for you here, just in case you forgot how to do that, right? So for this one right here, for the first part of the reaction, right, it's going to be NO concentration there, 2, right, Br, right, all divided by the NO Br, 2, right? And then for the other one, it's going to be the BrCl to the 2 divided by, I'm saying it slow because my pen's acting slow for some reason right now, Br2 inside of the brackets, and then Cl2 inside of the brackets, right? So this was K1 equals, and this one down here was K2 equals, right? So you can figure out the equilibrium. So in a problem, what would happen is you'd get like concentrations, right? You would get concentrations, and you plug them into the K1 equation to get the first equilibrium constant. You get more concentrations, right? To plug in here to get K2, right? Which is the second equilibrium constant. And all you do is multiply those two to each other, right? Those two to each other to get the overall, which is the K3 of the entire two-step reaction. Does that make sense? Right? Good stuff. Good stuff. So the last thing we're going to talk about is called homogeneous versus heterogeneous equilibria. Homogeneous equilibria occurs when the reactants and the products are all in the same phase, right? And then heterogeneous equilibria occur when something in the equilibrium is a different phase. Okay. So just a rule to take note of here, right? the value used for the concentration of a pure substance is always 1. Okay? The value used for the concentration of a pure substance is always 1. So let's take a look at an example. Here we have the decomposition of calcium carbonate, right? This is actually a heterogeneous equilibrium because we start out with solid calcium carbonate, it becomes solid calcium oxide, and then CO2 gas, right? CO2 gas. So the result is then we have our equilibrium constant equals the concentration of carbon dioxide, right, inside of this closed system right here. And then what that means then is that the equilibrium constant for pressure is then just the partial pressure of CO2 because it's the only one that's in gas phase, right? It's the only one that's in gas phase. So I wanted you to see what's happening here in this picture, okay? Here we have solid calcium carbonate, right? And it's going through a reaction where it's becoming CO2 and calcium oxide here, right? So here's the CO2 gas that's bouncing around, right? And here's the products being made, the calcium oxide, right? So here there's a large amount of calcium carbonate and a small amount of calcium oxide, right? And the gas pressure of the carbon dioxide is P, right? It's just P. So then we look at this one here. A lot of the calcium carbonate has already been converted over to the calcium oxide, right? So now there's more calcium oxide than there is calcium carbonate, right? What happened to the concentration or the pressure of carbon dioxide then? What happened to the concentration or the pressure of carbon dioxide? Nope. It stays the same. It actually stays the same, right? Does it look the same? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. There's still 9 molecules on both sides. Yeah. So the point of this is the fact that no matter how much Ca or calcium carbonate or calcium oxide you have, right, the pressure of the heterogeneous equilibrium gas will always stay the same. Does that make sense? Right? It will always stay the same. So you could have a little tiny bit of calcium carbonate and a whole bunch of calcium oxide. It will still be, let's say, 9 is the pressure, right? If you have a whole bunch of the starting material, this calcium carbonate, and just a tiny bit of product, calcium oxide, the pressure is still 9, right? Because I say 9 because that's how many molecules that they've shown drawn in there, right? So that's the point of this. Make sure you know that it stays the same, right? No matter what the concentration is of the solids or how much there is of the solid. So let me ask you this question, right? What happens if I let some of this out, like I pick up the cylinder, right, and let out some of the carbon dioxide? What will happen? Yes, that's true. It will reach equilibrium again, right? What happens to the calcium carbonate then though? Does it increase, decrease, or stay the same? It decreases. Why does it decrease? Did you say decrease? Awesome, awesome. Why does it decrease? Right, you gotta find the carbon from somewhere to make the carbon dioxide to reach equilibrium, right? Does that make sense? So I will ask you a question like this on an exam, right? I'll show you some pictures, and I'll ask you at the very end of it all, what happens to one of the solids if I let out the gas? All right? Everyone understand what's happening there? Good job, Stephanie. You got like 3 of those in a row right. 3 of my oral questions in a row. Awesome. I have no idea. This is your last question for today, and then we'll end the class. Last question for the day. Which of the following is an example of a heterogeneous equilibrium? I only got 8 responses. Still waiting for 4 more. Got 10. 2 more people. Might be a typo. I'll check on that for you. Okay, so the vast majority, everybody got that one. Most of them people got that one right. The answer is definitely A, right? Because if you look at this here, the only one here that has 2 different phases is the gas of calcium carbonate and the gas of carbon dioxide and the solids of calcium oxide and calcium carbonate. I was hoping to trick you, right, by having this one down here without any phases on it to see if anybody would pick that, right? I was hoping to trick you there, right? Right. That's a good point. It's a very good point. All right. So, deducing concentrations, right? So, how do you figure out what a concentration of a product or reactant is at equilibrium? And these are the steps that you have to take. And I'll go through these, one by one, and we'll figure it out all together, right? The first thing you got to figure out, right? The first thing you got to do is you got to tabulate all the known initial equilibrium concentrations, right? So that stuff is the stuff that's going to be in your problem, in the word problem that we give you. Okay. Okay. After that, for anything for which an initial or an equilibrium concentration known, you got to calculate the change, right? So that change means how much of the initial has gone away, right? Initial concentrations have gone away, and how much of the new stuff has come in, right? Has been made, and use the initial concentrations to find the equilibrium concentrations of all the species, and then calculate the equilibrium constant using the equilibrium concentrations. Okay, so these 5 things here, these are the 5 steps, and it seems a little complicated, but we distill it all down to this thing that we call the ICE table, and I'll show you what the ICE table is in a second. And I'll tell you now that the ICE table is the bane of every Gen Chem student's existence, because we'll use the ICE table for many, many things for the rest of the semester, right? But it's the easiest way to organize all your equilibrium concentrations, right? So one more time, tabulate all the known concentrations of the equilibrium and the initial. For anything for which the initial and the equilibrium concentration is known, calculate its change. Use a balance equation to find the change for all the other products and reactants. Then use the concentration and changes to find equilibrium concentration for all species. And then calculate the equilibrium constant using the equilibrium concentrations. Okay, so your first question for today is this. Which of the following steps are involved in deducing an equilibrium concentration? And it's an easy one for the first one. Most of the questions today will be easy. And while you guys are signing in, I'll sign in as well. Oh my God. I promise I work here. Just stop asking me for all this information. Three, 7, 9, 6. Yes, that is definitely me. Thank you very much. Thank you very much. Save, even though you never save. And then all my forms. Oops. That's already been done. Here it is, deducing K. We got 8 people responded so far. I'm sure there's more people. There's 10 of you in here? Yes, there's 10 of you, so we need 2 more people. One more person, please. There's still 10 people, though, right? Yeah. Still waiting for that last person. There it is. There's that last person. And that last person answered correctly. No, wait. I don't know who they did. Anyway, so I don't know if they did or not, actually. It looked like it changed, but it didn't change. Anyway, so the distribution is this. Which of the following is deducing the separate concentrations? Actually, the answer is D. All of them were steps in deducing the equilibrium concentrations. Okay, all of them were steps. So, and I know I have all these steps written out pretty clearly here for you, right? In this little spot right here, right? But let's go through and do an example of how to do a equilibrium concentration. All right. So here's an example of a question I might give you on a written portion of an exam, right? On the written portion of the exam, a closed system initially containing 1 times 10 to the negative 3 molar hydrogen gas and 2 times 10 to the negative 3 molar iodine gas, right, at 448 degrees Celsius is allowed to reach equilibrium. An analysis of the equilibrium mixture shows that the concentration of hydrogen iodide is 1.87 times 10 to the negative 3 molar. Calculate what Kc is, which is the equilibrium constant, right, at this temperature for the reaction taking place, which is this. Okay, so I was just saying before, right? This is when we introduced to you this thing called the ICE table, right? And it's the bane of all Gen Chem students' existence because we use it for almost every single thing from this point forward, right? And the reason why it's called the ICE table is because I stands for initial concentration, right? C stands for the change in concentration, right? And then the E stands for at equilibrium, right? Or equilibrium concentration. Okay, so the way you set up this ICE table so that you can answer so many different questions in life, I guess in your chemistry life rather, right, is you put the reactants over here on the front end right here. So these are all reactants, right? And then this is the product. Product. No, product. Oh, well, I'll just cross it out and write it correctly. How about product? There we go. That's the product of this reaction. Okay, so we've got hydrogen gas up there, and that's in molar. We've got iodine gas up there, that's in molar. Those are the 2 reactants. And then over here we have the product, which is hydrogen iodide gas, and that's in molar as well, and that's our product, right? And then the way we fill out this chart, this ICE table, right, is we fill it up with the things that's been given to us. Okay, the things that have been given us, right? So we go back to our problem here. It tells us that the initial concentration of hydrogen gas is 1 times 10 to the negative 3, right? And it tells us that the initial concentration of iodine gas is 2 times 10 to the negative 3, right? So that's what we put there. Okay, we put here initially, right, for hydrogen gas, 1 times 10 to the negative 3, and initially we have 2 times 10 to the negative 3, right? And then, of course, since this is initial and no reaction has occurred yet, what do we put here for concentration of hydrogen iodide? 0, right? Because no hydrogen iodide has been made yet at the initial step, okay? And then the other piece of information that we're given is that when the reaction goes to completion, or not completion, but goes to equilibrium, right, the concentration of hydrogen iodide gas is 1.87 times 10 to the negative 3. And so this number here is what goes here, right? Because at equilibrium, hydrogen iodide gas, right, is 1.8 times 1.87 times 10 to the negative 3, right? So that's how you start out doing an ICE table, okay? You plug in all the stuff that you know. Okay? The next thing you can do is you can start filling in the rest. So what's the change here then, right? What do we put in change? Well, we know that we began with 0 moles, right, or 0 molar hydrogen iodide gas. And at equilibrium, it was 1.87 times 10 to the negative 3 of a hydrogen gas. I'm sorry, not hydrogen gas, hydrogen iodide gas, right? So then we know that the change, right, the change from 0 to this is that same number because you went from 0 to 1.87 times 10 to the negative 3. So the change is then plus, right? The change is then plus 1.87 times 10 to the negative 3, right? Because you're getting more of it, and that's why it's plus. That's why it's plus, right? So right now, I'm going to go ahead and tell you that when you're doing these ice tables, just remember, this is ice, right? And this is always reactants right here. And this is always the products right here. And so generally, you always divide it down the middle like that. Sometimes there'll be less or more, right? Reactants or products, but we always divide it down the middle. And the reason why I do that is because if this is going to be the side where you get stuff, right? Because it's the product side, you know, the change is positive, then that means over here on the left side, these changes will always be negative, right? These changes will always be negative because you're losing, right? You're losing hydrogen gas and you're losing iodine gas, right? You're losing iodine gas. So how do we figure out then? How do we figure out then what these changes are, right? For equilibrium concentration for the hydrogen gas and the iodine gas? Well, we got to go back to doing our molar calculations, right? Remember our molar calculations from Gen Chem 1? Okay. So we'll do hydrogen gas first, okay? We're told that at equilibrium, right, we have 1.87 times 10 to the negative 3 concentration moles of hydrogen iodide, okay? So we can start out by saying that. 1.87 times 10 to the negative 3 moles, right, of hydrogen iodide, right? But remember when we say molar, like big M molar, what does that actually mean? That means number of moles over liters, right? That's a concentration. So we can easily put it over 1 liter right there, right? Just like that, okay? And then we continue our fence posts or our dimensional analysis, right? For every, so remember that also the equation is right there too. So don't forget your stoichiometry, right? For every 1 mole of hydrogen gas, you get 2 moles of hydrogen iodide. For every 1 mole of iodide gas, you get 2 moles of hydrogen iodide, right? So don't forget that you have the stoichiometry right here. Those are all ones. That's a 2 right there. Okay, so going back to our dimensional analysis, right? We have to get rid of moles somehow. How do we get rid of moles? Well, for every 2 moles, right? Every 2 moles of hydrogen iodide, right? For every 2 moles of hydrogen iodide, we get 1 mole of hydrogen gas, right? And that will give us a number. And we have to do the same exact thing again for the iodine gas. Now we're lucky in this problem because both the iodine and the hydrogen gas have 1s as their coefficients. So they're probably going to come out, not probably, they will come out to the same number. But it's not always like that, right? It really depends on the stoichiometry. But just for giggles, 1.87 times 10 to negative 3 molar. Oh, I forgot to put HI up there. HI, right? 1 liter, okay? And then for every 2 moles of HI, we get 1 mole of I, right? And then that gives us a number, okay? That gives us a number. That gives us a number. And I won't ask you to do the calculation for me right now because I did it already. Actually, I had a calculator with me. Oh, I gave it to Kimberly. That's all right. She's got my calculator, but that's okay. This should come out to be 9.35 times 10 to the negative 4. And this one should also come out to be 9.35 times 10 to the negative 4, right? So those right there, right, are the changes in the concentrations, right, for both hydrogen iodide and for, no, sorry, not hydrogen iodide, for hydrogen gas and iodine gas at equilibrium. So we already know that this is supposed to be a negative sign right here, right? Because that's what we're losing. And then we put into our box 9.35 times 10 to the negative 4, 9.35 times 10 to the negative 4. Okay? Does that make sense? How we get those numbers right there? Right? Easy little molar calculation at the bottom that you've done a gazillion times in Gen Chem 1, right? Right? Easy little molar calculation to do the change in the reactants. Okay? So to make sure that I'm right, I did already go forward and typed it in for you so you could read it better, right? So there we go. It's 9.35 times 10 to the negative 4, negative 9.35 times 10 to the negative 4, right? Sounds good. Sounds good. So now the question is, right? Now the question is, how do we figure out what's at equilibrium then? Anyone know? What is the concentration then of hydrogen gas and iodine gas at equilibrium? Exactly. That's exactly right. You just subtract this number from that number and this number from that number, right? Because of this, these are the changes, right? That's what's missing. That's what's going away, right? And so all you have to do is subtract 9.35 times 10 to the negative 4 from 1.00 times 10 to the negative 3, and then also do the same thing over here. Subtract 9.35 times 10 to the negative 4 from 2.00 times 10 to the negative 3, and then you get the concentrations at equilibrium. It's a great time, right? And so doing that calculation gets you this, right? So now you have a completed ice table, right? It's a completed ice table that shows you the initial concentrations of the reactions, shows you the change, right? And then at the equilibrium, it shows you what the concentration of each is. At equilibrium, the concentration of hydrogen gas is 6.5 times 10 to the negative 5. Iodine gas is 1.06, 1.065 times 10 to the negative 3. And then we already knew this from the question, right, which is 1.87 times 10 to the negative 3 for the concentration of equilibrium at hydrogen iodide, okay? Which is great, right? Which is great. The rest of it is easy because the rest of it is plug and chug. If you recall from the last lecture, right, the equilibrium constant is always what? There's always, equilibrium constant is always the products over the reactants, right? Right? The equilibrium constant is always the products over the reactants, okay? And remember that we had 2 moles of hydrogen iodide gas. That's why it's squared at the top, right? And then for each of the moles of hydrogen gas and iodine gas, they're all 1 each. So they're at the bottom, right? Literally, that's all it is. Products over reactants, right? Don't forget that. That's important, right? And all we have to do now is plug in these numbers here, the equilibrium numbers, right? Plug in those equilibrium numbers right there that we got at the bottom into this equation, right? Into this equation. So that's a 1.87 times 10 to the negative 3 squared. Don't forget the squared, right? And then that's the equilibrium concentration of hydrogen iodide at the end of the equilibrium. And then we have the concentrations of both hydrogen gas here and iodide gas, right? Iodine gas there from the bottom of the ice table, right? Just to remind you, this is the H2 concentration at equilibrium. This is the I2 concentration at equilibrium. And this was the HI concentration at equilibrium, right? And you just do that math, right? So don't forget please excuse my dear Aunt Sally, because you're going to get this wrong if you don't follow the order of operations. You have to square this first, right? So square these numbers first. Then you have to multiply these numbers by each other first, right? And then you divide them, right? Because the order of operations is that multiplication comes before what? Division does, right? So don't forget to do it that way. Otherwise, you get the wrong answer. All right, so here's your next question. How do you determine the change in H2 and I2 in the ice table? It's the same as HI by subtracting HI from the initials by carrying out the molar concentration calculations using stoichiometry, or none of the above is correct. Okay. Let's see here. There we are. Got 3 responses so far. So far, most of you are getting it correct. Still need 3 more people. 2 more people. Two more people still. 1 more person. One more person, and they're there. Okay. Wow, we got an answer for every single one of them this time. All right, so here's the distribution. Here's the distribution right here, right? All 4 colors are present right now, but that's okay. The vast majority of you got that one correct right there. The answer is in fact C, right? The answer is C, because if you recall from the previous slide when I was going through this whole thing, right? To get the change in I and H, right? You had to go through your molar calculation using stoichiometry to get those numbers, right? So the other answer that was there was subtracting from the initial. Remember that? That doesn't happen until after you get these numbers, right? And that's finding the equilibrium concentration. So finding the change requires the stoichiometry calculation. Okay. Any questions so far? I know this is riveting stuff. It's good stuff. Okay, so let's keep on trucking along here. Is a mixture in equilibrium? Is a mixture in equilibrium question? Okay. Which way does the reaction go? Okay. To answer these questions, I get you. They're 2 separate questions. Okay. Is the mixture in equilibrium? That's the first question. Which way does the reaction go? That's the second question, right? So to answer these questions is we look at this thing called Q, right? This thing called Q, and Q stands for the reaction quotient, right? It stands for the reaction quotient, and Q actually looks a lot like the K, the equilibrium constant, right? But you use Q to figure out concentrations at certain conditions, right? At current conditions, not necessarily at equilibrium, but at different times, different points of the reaction. Okay. To calculate Q, you have to substitute the concentrations or the pressures of the reactants and products at any given time during the reaction into the equilibrium expression. So don't get confused, right? The Q expression is going to be the exact same thing as the KEQ, or the equilibrium concentration expression. The only difference is that for K, you'll have the concentrations of all the equilibriums, right? Whereas for Q, you'll have the concentrations that are given to you at a certain point in the reaction. Okay, so those are 2 different things, and we'll go over an example in just a second. So nature wants K to equal Q. Why? Because Q is equilibrium. Sorry, K is at the point where it's equilibrium, right? And so everybody wants to be at equilibrium, right? They're most stable that way, right? The reaction is, effectively over, right? You've got the same rate of reaction forward and reverse, same number of concentration of products and reactants, right? So everybody or nature wants Q to equal to K, right? So if Q is less than K, nature will make the reactions proceed to the products, right? So here's an example right here. And here's Q. It's less than K, right? So it's going to push your reaction to go towards the products, okay? If K is equal to Q, or Q is equal to K, then the reaction is in equilibrium, right? So there we go, right there. There's Q equal to K, and here's the products and for Q and for K, and they're both at the same point, the equilibrium point. And then on the other hand, if Q is greater than K, nature will proceed to make the reaction go reverse so that you can get closer back to equilibrium. Okay? So let's just remember this part right here, the takeaway message here, right? If K is less than Q, let me say that one time. If Q is less than K, then more products are going to be made. If Q is equal to K, you're at equilibrium. If Q is greater than K, then more reactants are going to be made, right? You're going to go the opposite direction, okay? So calculating equilibrium concentrations, right? So we'll go through an example of that in just a second, right? But if you want to know what the equilibrium constant is, you can find equilibrium concentrations from the initials and the changes based on stoichiometry, which we saw that in the previous example, right? You will set up a table, another ICE table, and use the one used to find the equilibrium concentration, but the change now will all have x's in it, where you have to solve for x. And I'll show you how to do that in a second. But before we do that, here's your next question. What does nature want? Does nature want Q to be less than K, Q to be equal to K, Q to be greater than K, or none of the above? Oh, I love this stuff so much more than what I'm teaching in my other class. I don't know if you knew this, but I'm teaching uh, a science class, like a general education science class too, in addition to this one here. And right now we're going through, we're learning about electrical motors and magnetism and stuff. And I'm like, oh my God, this stuff is so boring. So if you come to my office and I'm like looking like I'm stressing out with my like face palming and stuff, it's because I'm having to relearn how to do magnetism. It's crazy. I had a terrible physics teacher, so Dr. Walker, that guy. I don't know if you remember this from physics, but there's this point where you have like an electrical current like that, right? And it's going in that direction. And then to show that there's a magnet going, like a magnetic field going, they'll use like X's to show that it's going into the board, and dots to show that it's coming out of the board, the magnetic field. And so these are supposed to represent like tail feathers, as a feather, a tail feather, an arrow is flying through the air. You look at the back of it and you see tail feathers, you know. And so Dr. Walker was drawing those tail feathers X's to show the magnetic field going into the board, and then he kind of stands back and he's like looking at it, and we were like, "What the heck is he looking at?" And then we asked him like, "What are you looking at?" And he starts laughing, just ha ha ha, ha like megalomaniacally, like laughing. And we're like, "What are you laughing at? Why is this so funny to you?" And he's like, "Oh, I'm just practicing for your exam, meaning all the X's." So that rat bastard. I did not like Dr. Walker at all. He did not make my experience in physics very fun. So, see, at least I don't do that to you guys, right? If anything, I, make fun of myself. Okay, so let's see how everybody did on this question. Uh, is that it right there? Q, yes. 10 people answered. And yes, very good. The vast majority have got that one correct there. Only one person got that one wrong. Q needs to be equal to K. That's how nature wants it. Okay? So here's our example. And again, I don't know if you remember Miss Dickens telling you this before, but it's a good time to brush up on your algebra because we'll be using it a lot for the rest of the semester. Um, Buckle up, because it's going to be crazy, right? We have a 1 liter flask. It's filled with one mole of hydrogen gas, right, and 2 moles of iodine gas, just like we did before, right? Given a K of 50.5, right, at 448 degrees Celsius, what is the equilibrium concentration, right, of hydrogen gas of iodine gas and hydrogen iodide, right? So just given these things, so you should be able to figure it out. So here's our original ice table, like we saw a second ago, right? Remember that ice is I for initial concentration, C for changing concentration. Some people actually use a triangle to denote change, and then E is for equilibrium, okay? And then of course here we have the reactants again, right? These are the reactants. And here we have the products. And you do what you did before, right? Where you fill in, or the products, you fill in what you know, right? And so initially, 1 goes there again, right, for the initial for hydrogen gas. 2 goes there, right, for the initial of iodine gas. And then 0, because it hasn't happened yet, right? Nothing's happened at the initial. So 0 goes there for hydrogen iodide gas. But we have to solve for everything else, right? We have to solve for everything else, right? So we then know that, remember I told you this on the last one, right? We split this down the middle like that, right? We know that everything over here on the left side is going to be negative, right? And over here, everything on the right side will be positive, right? And so what X is, right? What X is then is the amount of change, amount of molarity that this hydrogen gas is going to lose. That's why it's minus X. Same thing here, minus X, right? Minus X, because it's the amount of molarity that this X is going to lose, right? Or this iodine is going to lose, right? So it's minus X. But then since we know that it's 2 moles of hydrogen iodide for every mole of iodine and hydrogen, right? It's 2 plus X, 2 plus X, plus 2X here, right? Plus 2X here, because there's 2 moles there, right? So it makes sense, because if you're losing X here and you're losing X here, you have to gain an X over here, right? And since it's so that's why it's a plus X, but the reason why it's a 2X is because there's 2 moles of hydrogen gas. And then what that means then at the end of it all, the equilibrium concentrations can be solved using these equations, quote unquote. The equilibrium concentration for hydrogen gas is going to be 1 minus X, right, which is the initial minus the X. And then iodine gas will be 2 minus X, which is the initial minus X. And then here, it's just going to be, since you were at 0 for hydrogen iodide, and you're doing plus 2X here, then the concentration at equilibrium will just be 2X, right? Just like that. It's good stuff. It's good stuff. So in our example then, again, we have to do our, our equilibrium constant equation, right, expression, where we have the products, right, the products over the reactants, right, products over the reactants here, right, and if we notice, it's the exact same thing that was at the bottom of the ice table right here, right? We had 1 minus X for the hydrogen gas, so, so there we have the 1 minus X for the hydrogen gas, right? And then we had the 2 minus X for the iodine gas right there, okay? And then we had the 2X for the hydrogen iodide gas, which is right here, okay? And then we were given in the problem that it has a K, or an equilibrium constant of 50.5, and that's why we set it equal to 50.5 here. So now what we have to do is solve for all these X's, right? Got to solve for all those. So I'm going to ask you now, how do we solve for those X's? How do we solve for these X's? Say again? That's true. You do have to start multiplying. It's actually called foiling, right? Remember that from high school? FOIL? Close. There's a square root involved. So this is what we call a binomial equation, right? And in a binomial equation, you have to use what to solve for it? The quadratic formula. Do you remember the quadratic formula? Very close. And
Negative b plus or minus square root of, I don't know what's in the.
I'm gonna give you a chance to say it before I actually write it out there.
So it's the square root something minus 4ac
Uh-huh.
divided by
2a. That's
2a,
right.
yeah.
Good, good. So the hodgepodge of all you putting that together got it right. So good job there. All right. So there's a couple of things you got to do first before you can actually put it into the quadratic equation, right? Because right now it's an expanded thing, right? And remember that the quadratic formula requires that you have this format. A equals x, it's not A equals x squared. A x squared plus x bx, right? Plus c equals 0, right? It has to be in that form for you to be able to use the quadratic equation, right? It's got to be in that form. Because just like you all said all together, right? The equation is x equals minus b plus or minus the square root of b squared, excuse me, minus minus 4ac, all divided by 2a. Okay? That's the quadratic equation. Okay? That's the quadratic equation. So the difficult thing about this, right? The difficult thing about this will be trying to get this, right? Trying to get that whole thing into the ax squared plus bx plus c equals 0 form, right? That would be the most difficult part of this problem. Okay? So, right? So what do we do first? Okay, well the first thing we should do, right, is try to get it so that we actually have something that equals 0. Okay, we have to make it so we have something that equals 0, right? Because right now we have you can this part right here is just the expression, right? So really this is the math part right here, right? That's the math part right there. This is the chemistry part, and this is the math part, right? And so really you're going to be working with just this part right here, right? Not the chemistry part, but the math part. Okay. And so when you have it like this, the first thing you got to do is just like Stephanie was saying, the first step is to foil these two to each other. Okay, do you remember what foiling means? Yes, exactly. Right? So, easy as pie, okay? First thing here is we'll do the let me think about this just 1 second here. Okay, yeah. So we'll do, I always like to make it start out looking like the quadratic equation. So the first thing I'm going to do here is I'm going to multiply x times x, right? Because that makes it x squared, okay? And then I'm going to do 1 times x, right? And then 2 times x, right? And both of those are minus x's, right? So that's minus 1x minus 2x, right? Make sense so far? You ever got that so far? Right? And then the last thing to do is the 1 times 2, right? Which is going to be the plus 2. Okay? And then you still have it equal to, so that part right there is this, right? That comes down to that like that. So now you have this. Oh, I'll go ahead and do this part right here too, where I have to square that up there, right? The 2x squared, right? So all that comes down to looking like this. 4x squared all over x squared. We can combine these two together, right? Oops. Should be negative 3x plus 2, right? And all of that is equal to what? 50.5, right? Oh, say again? Right up here. 2 squared. Yeah. Okay. Everybody got that so far? So now, I don't know about you guys, but the ax squared plus bx plus c equals 0 doesn't have a fraction in it. So we've got to get rid of the fraction somehow. How do we get rid of the fraction? Exactly. Multiply both sides by the entire equation. Right? There. And then you're also going to do the same thing over here, which I ran out of room, but you get the idea. Oop, that should be a minus. Plus 2. Right? So what does that do? That cancels out these down there, right? And now you have 4x squared equals 50.5 times x squared minus 3x plus 2. We're almost there, right? We're almost to the point where we have it equal to 0. Now what do you have to do? We were trying to solve for x, yes. Anybody know what we're doing next? Well, the next step in this is to multiply out the 50.5 to the quadratic formula, not quadratic formula, the binomial equation, right? So you got to multiply 50.5 times this, 50.5 times this, and 50.5 times this, right? So that gives you, I'm going to move over here so I have some room. 4x squared equals, the first one is easy because it's just 50.5 x squared, right? And then minus whatever minus 3 times 50.5 is, which is 151.5x, and then plus whatever 50.5 times 2 is, which is 101. Right? So far, everybody got it? Right? Has everybody got it so far? Okay, now I'm at this point. What do I have to do now? What do I have to do now? Keep going. Say again? Subtract 101? There's an easy, what is the point of this whole thing to get it to? So you can use a quadratic equation, right? So what would you need to do to get it to do the quadratic equation? You've got to get it so it's equal to 0. So what do? What about 4x squared? So why, let me ask you this. If you're looking to have a 0 at the end, why do you want to divide it? Right, but you can't use it just yet because it's not equal to 0. So the way you get this to equal to 0, what do you do to get something to 0, anything to 0? Subtract it, exactly. So subtract minus 4x squared on both sides. I told you we're going to do a lot of math now. Class? That's great. It's going to be perfect for you then. You're learning it here and you're learning it in your other class. Right? It's great. So we do that, right? We subtract both sides. That makes it so this side over here equals 0 already, right? So this is, I'm running out of room, so I'll just write it over here. So the left side now equals 0, right? And now the right side equals what? What is 4x squared? What is 50.5 x squared minus 4x squared? 46, exactly. So 0 then equals, right? 0 then equals 46.5 x squared, and the rest of it stays the same. Why can't we do any more subtracting? So I can't hear you. Say that one more time. Exactly. That is exactly right. We've already combined all like terms, right? Because x squared is a like term, x is a like term, and then there is no thing for that one, right? And so now you have this equation right here, which is great because now it's in the form of what? Ax squared plus bx plus c equals 0, right? Good stuff. Good stuff. I tried to warn you guys, right? We're going to be doing a lot of math.
Yeah, this is the sort of stuff I don't like to be on quiz for 10 minutes.
Well, if you're really good at it, it actually goes by really fast.
Five questions, 5 minutes, and they're all short.
I mean,
Major, change in my major.
okay, so now let's solve for x. Okay, let's solve for x. Now let's solve for x. Okay, so I'm going to erase some stuff here so I have some room. If that's okay with you guys. Maybe not, because that might confuse you some more. Okay, so now we can use the quadratic equation, which is right there, right? So it should come out to be this. X equals, right? And I'm using this one again just to make sure, the quadratic equation right there, right? Minus 1, negative 155.5, okay? Don't forget the plus or minus part, okay? The square root of, again, negative 151.5 squared minus 4 times 46.5, because that's A, times 101, because that's C, right? All of this is divided by 2 times 46.5. So now all you have to do is plug that in your calculator and figure out what the answer is, okay? I'll try to make so that you can see this on the notes. Separate all this out for you. There we go. Okay, all you have to do is plug that in your calculator and you can figure out what that is. And see, the thing about it is that I cannot stress enough how important it is for you to do. Please excuse my dear Aunt Sally, or the order of operations here, okay? Okay? You should get 2 answers. One of your answers is going to be, well, actually, if you're calculating it, let me see. And don't worry, if you don't have a calculator for the exam today, Ms. Dickens will have a box of calculators for you to use. But you absolutely can't have a phone, right? All right, I'm going to go ahead and give you the answers, and you try to do this and see if you get the same thing, okay? You're either going to get x equals 2.323 or x equals 0.935, okay? So far, so good. Are you guys getting the same answer? Let me make sure I'm still recording here. Are you still recording? Are you still recording? Yes, you are still recording. You can still hear me. Okay. Don't forget to use your parentheses. Don't forget to use your, things. Okay. As soon as someone tells me that they have a similar answer to mine, I'll move on. Did you get a similar answer to mine?
I got the same answer.
Good. Did you actually use did you actually do the quadratic equation piecemeal like that, or did you use the binomial function on your calculator? If you didn't know this, a graphing calculator actually solves quadratics, binomials, quadrinomials, trinomials, and all you have to do is plug in the A, B, and C. Yes, they can. But that's the reason why you're not allowed to use them on exams, right? I'll show you later. But yes, there is a function on graphing calculators that allows you to just plug in. Yeah, all you do is plug in the A, B, and C, and it calculates it all for you, right? But it's important that you do it this way because that's how you're going to be doing it on the exam. You're not allowed to have a graphic calculator on the exam. All right, so Naraya's told me that she's got the same answer as me, so we can move on. Let me ask you this question now. Which is the correct answer? Oh, first question is, why do we get two answers? Huh? We do have a plus or minus. That's the one reason why. But what's the other reason why? What does the graph of an exponential equation look like? A binomial equation look like? It's a parabola, exactly, right? It looks like this. Someone knows stuff, right? I know what she's talking about, right? It's either going to be like this, right? Or it's going to be like this, right? And when you're solving for x, you have an x there, and an x there, or an x there, or an x there. And so you have two x's you get, right? That's why there's a plus or minus. Make sense? So how do you know which one's the right one for the chemistry part of the question? Right. Yeah, because like once you get over here, right? It tells you right here that you have only 2 moles of this and 1 moles of this, right? And this is a change, correct? That's a change. You have to minus that. And one of your answers is 2.32. Is it possible to subtract 2.32 from 1 molar or from 2 molar? No, because you don't have that much, right? So what's the correct answer then? Yes, the correct answer is 0.93. Oops, forgot to put the drawing mode. So the correct x is this one, right? The correct x is the 0.935, right? Does that make sense? That's the correct x. The incorrect x is that one, right? Because it is physically impossible for you to subtract 2.323 molar from an initial concentration of 1 molar or initial concentration of 2 molar, right? So it's always going to be the number that's less than what your initial concentrations are. Does that make sense? It will always be the x. The x will always be the x that is lower than your initial concentrations. Okay? Think about this, right? In math, they just give you numbers and you just figure things out. But in chemistry, it's about problem solving, right? So you've got to use your common sense and figure out what's not possible and what is possible, right? It's not possible to subtract 2.323 molar from 1 molar or from 2 molar. But it is possible to do what? Subtract 0.935 molar from 1 molar or 2 molar. Does that make sense? You've got to think about this in chemistry terms, okay? So, good stuff, right? So just like Narayan just said, let's plug it all in. Okay, let's just plug it all in. Right? Since x must be subtracted from 1 molar, 2.323 makes no physical sense. You get a negative concentration. Crazy, right? Absolutely crazy. Okay? So the value must be the 0.935. So in the end, all you have to do now is subtract that change from, because remember the equations were, right? Remember that it was in the ice table, for this one right here, it was 1 minus x, right? And this one was 2 minus x, right? And this one was what? Remember what this one was? For hydrogen iodide? It was just 2x, right? Okay, so all you do now is you plug in the 0.935 into that x, into that x, right? And when you do that, you end up with your answers, your equilibrium concentrations, right? You end up with your equilibrium concentrations. Isn't this amazing? It's amazing stuff. It's so cool, right? It's so cool. And you know why else it's so cool too, right? Because when you look at what it was originally, right? This is what you had right here as the equilibrium, right? You had all these x's right there as your equilibrium. You come over and do the quadratic equation, right? And then you get these answers here, right? And look at that number right there, right? It's actually off the order of magnitude of the same number, 1.87. Isn't that crazy? Crazy stuff, right? Crazy stuff. Okay. All right. Any questions on that? That was mostly quadratic stuff and math stuff, right? Any problems? Any questions on where that comes from or anything like that? I expect the people that just came into the class are probably gonna have to watch the video for this one, right? So, good luck. But no, I explained it great. I promise. I think I did anyway. It's just basic algebra, okay? So, here is your next question. When solving for x, what mathematical formula is used? When solving for x, what mathematical formula is used? I've got 8 responses. I'm waiting for 4 more. 4 more responses. 3 more. 2 more. 1 more. Okay, I've got everybody's responses. What is the correct formula to use to solve for x? Quadratic equation, exactly. Right? Quadratic equation. All right. In talking about that, we have this thing called Le Chatelier's principle, okay? And Le Chatelier's principle says this: if a system at equilibrium is disturbed by a change in temperature, pressure, or a component of the concentration, the system will shift its equilibrium position so as to counteract the effect of the disturbance. So what does that actually mean? What does that mean? Well, I forgot to, sorry, what? I forgot to play the song here because this is your welcome chart, right? This is a chart that actually tells you what happens with Le Chatelier's principle and when you do things to a system, right? Did I bring my hat? Yeah, I did. So if you take a look at what's happening here, right? Right now, let's say we have initial equilibrium, which there's an equal amount of reactants and an equal amount of both reactants, right? And so it goes to equilibrium, right? Well, Le Chatelier's principle says when you add more substances that are reactants, what happens? It moves towards making more products, right? Or on the other hand, right, if you add more products, it goes to making more reactants. But the point is, at the end, the equilibrium is reestablished. And we saw that already before when I was talking about the gases mixing together. It didn't matter what concentration of gases you had, right? Whether you had more of one, less of the other, or more of that one and less of the other, it all regains equilibrium in the end, right? But what Le Chatelier's principle says is that the more products you put in, the more reactants you get, right? Or the more reactants you put in, the more products you get. And then equilibrium is reestablished, okay? Equilibrium is reestablished. So notice when we added more reactants here, right? When we added more reactants here, when the equilibrium was reestablished, we actually end up with more products, right? We end up with more products, okay? So that's what happens when you do Le Chatelier's principle with, modifying the concentrations of things. Okay, so let's talk about it with pressure now, right? Say you have an initial pressure, right, sorry, an initial volume, right? And this is the pressure at this, the pressure is in equilibrium at this initial volume, but then you squish down the volume, right? The volume gets smaller, right? The system shifts so that there are fewer, shifts direction, so of fewer gas molecules. So it can accommodate the pressure, right? It can accommodate the smaller volume. So you saw that when we were talking about, um, what was it again? It was calcium oxide, calcium, so what was it? Dang it, I can't remember now. What was that example? I remember the calcium carbonate, maybe? Yes, that's what it was. Calcium carbonate. Remember that? So calcium carbonate was a solid, right? And if you left it in the little thing, in the little beaker, right, in the closed system, right, it would become uh, it would become carbon dioxide and calcium oxide, the solid. Remember that? And then I said if you lifted up the thing and opened up and let some of the CO2 out, right, what would happen? You'd make more what? Carbon dioxide, and you would get less calcium uh, carbonate, right? Well, this is the exact opposite. Instead of letting stuff out, right? Instead of letting stuff out so that there's more carbon dioxide being made, right? Because there's less pressure in there now. If you're increasing the pressure inside because you're making the volume smaller, right? If you're making the volume smaller, then there will be less carbon dioxide made and there'll be more of the solids left to accommodate the new pressure, right? To accommodate the new volume. You remember that from the calcium oxide, calcium carbonate, and carbon dioxide example. I think this was in this. Was it in this PowerPoint? I'm pretty sure it was in this PowerPoint. I should have just had that up when I was talking. There it is, right there. Right, that one. Calm down. There we go. Yeah, remember this one? It was this example right here. So think about it like that, right? Think about it. I asked you the question, what would happen if you lifted it up and all the CO2 left? What would happen to the concentration of CO2 and what would happen to the amount of solid calcium carbonate, right? Well, it would start shrinking the calcium carbonate to make more CO2 to reestablish the equilibrium, right, of the CO2, right, in the flask, right, or inside that closed container. But say you didn't let it out, right, and you put more in there, right, and you actually decrease the volume, what would happen is that it would move so that there would be less gas, CO2 in there, and it would become more solid stuff. The exact opposite of the question I asked you the last time, right? So that's what that particular part of Le Chatelier's principle is talking about. Come on, you can change. Oh man, it was working so well. Everybody remember that one? Remember that slide? That was a messy one, wasn't it? That was a messy one. So that's what's going on here with the pressure part of Le Chatelier's principle, right? And then when we talk about temperature, right? Of course, when we talk about temperature, it can be either endothermic or exothermic, right? But if you increase the temperature, the reaction shifts to the right. If you decrease the temperature, the reaction shifts to the left, right? And in an endothermic reaction, and in an exothermic reaction, if you increase the temperature, the reaction shifts to the left, and then if you decrease the temperature, the reaction shifts to the right. Okay, so many multiple choice questions I will ask you in the assignments and in the exam and in the quizzes, right, will revolve around this slide here and this particular you're welcome slide here, and I'll give you a scenario, right? I'll give you a scenario like I have this reactant. I'm going to react it with this reactant. What will happen if I add more of this stuff? Or what will happen if I I increase the pressure? Or what will happen if I increase the temperature? What happens if I decrease the temperature? And you have to tell me what's going to happen, right? And that's the kind of multiple choice questions I'll ask you. And literally, it's all going to be answered by this slide right here, okay? By this chart. So this is the you welcome chart for Le Chatelier's principle, right? So you don't even have to really remember the words that much. Just remember these pictures right here, right? Because I'm not going to give you this on the exam, but it's pretty obvious because all you have to remember is that no matter what you do to a system, right, The Chatelier's principle says that it has to if you do something to a system, it has to re-equilibrate, and it will do whatever it takes to re-equilibrate, right? So adding in more reactants means you're going to get more products. Adding in more products means you're going to go back to reactants. If it's endothermic and you're increasing the temperature, it makes more products. If it's endothermic and you're decreasing the temperature, it makes more reactants. If it's exothermic reaction, right, then it's going to increase the temperature, you get more more reactants. If you're going to decrease the temperature, you get more products. So the one thing that you need to recall from like the very first, maybe second day, I don't remember what like lecture, very early on, is how do you tell whether a reaction is endothermic or exothermic? Does anybody remember? Yes, exactly. I will give you a delta H, right? And the delta H, if it's negative, it's what? It's exothermic, right? And if the delta H is positive, it's what? It's endothermic. That's how you tell the difference. Okay? You won't be able to tell just by unless you're super awesome. You know, you could just look at the reactants and you've done the reaction before and you've seen it get hotter when it gets done, right? Then you know it's exothermic. But if you're just looking at a whole bunch of atoms and they're being put together and they make some kind of product, you're not going to be able to tell whether or not it's exothermic or endothermic. So I would have to give you something to tell you whether the delta H is negative or positive. Does that make sense? Yeah? Good? Okay. So, whew, gases, more gases. So a change in reactant or product concentration. If a system is in equilibrium, adding a reactant or adding a reaction component, which is a reactant, right, will result in some of it being used up. Removing a reaction component will result in some of it being produced, right? So what that means is that I already told you if you add in more reactants, you'll get more products. So how do you get more products? It's because some of those reactants get used up, right, that you add in there to reestablish equilibrium. Well, on the other hand, right, I was saying how if you add more products, right, if you add more products, it makes it shift to the other direction, making more reactants. But how do you add more products? I thought you were trying to get more products to begin with, right? Well, the reason why you have more products is because you take some of the reactants out, right? And then now you have more products than you do reactants, and then it will shift to make it more reactants. Does that make sense? Right? Like, why would you be doing a reaction where where you're making some stuff, and then somewhere on the side you're gonna add more stuff, right? That doesn't make any sense because you're making the stuff already, right? Like if you had the stuff on the side, why are you doing the reaction to begin with, right? So the only way to make it go backwards, to make it reversible and go backwards, is so that some of the products become the reactants. It's going to be where you take some of the reactants out, right? So for example, if that were a gas, you lift up the container and some of the gas escapes, and then you make more reactants. Does that make sense? Right? Good stuff. Good stuff. Let's see here. Come on. Am I too far away from this thing? Is that what? Oh, first question. Will the addition of reactants result in, oh, well, actually, what will the addition of reactants result in? Apparently, I'm not very good with attendance because they keep on sending me mean emails about my attendance. Like, not that you guys aren't coming to class, it's that I'm not, like, reporting it. So, and it's not that hard. I mean, there's only 12 of you in here. I mean, I can look at the room and see who's here and who's not. So, and most of you come every single day. Oh my God, I have to do this thing again. Stupid. Stupid, stupid, stupid. Um, sorry, I got to put in my freaking, what is it, to dual factor authentication here to get logged in. Finally, Jesus.
So like, if this her pants
What happened?
short is like to your ankle,
Shorts?
her pants. Like it says a size short and then a size long. Short is like above your ankle.
I have no idea what you're talking about. Are you talking about in lab?
It's not chemistry related. Talk about pants.
What about pants?
Like when it says like a size and then short and then another the same size but long.
Oh, I thought you were talking about like what you have to wear in class or something or in lab.
No,
So,
short like above your ankle.
got you.
I've never heard
No,
of that.
so guys, like for example, when we buy scrub pants, right? We have like large regular, large short, large long. So large short is for people who are shorter,
Like
and then
petite or like.
huh?
Oh,
Yeah,
very good.
and then large long is for people who are taller, and then large regular or it's for people who are like normal, like me, like normal height, you know?
You're calling me short, eh?
Yeah, so that's what they call it. So, like for example, these are these are large regulars right here, right? So these pants I'm wearing right now are large regulars.
I never understood why it says regular size and then it says the size short and then size long.
Yeah,
What does that mean?
yeah. It's because well, because you can't fit everybody into just three sizes, you know. So luckily, I'm a pretty average height, so I wear like normal clothing. But there's some people that are like my weight and a lot taller. So they have to have like the large waistline, but they also have to have longer pants. Otherwise, they're flooding the whole time. Is that a word people still use? Flooding? It's when you show your socks, you know?
Yeah.
Yes, exactly. That's what I'm talking about.
And I'd be like, if you don't go back in that room and take off the mic,
All right, 12 people responded, and the vast majority, not the vast majority, just some people. Um, let's see here. 7 people, I think. Okay, so actually, this is interesting, right? It's actually the answer to this question would actually be D, all of the above. So the D's have it. The vast majority got it wrong this time, but I'll chalk that up to you guys writing your pre-labs or something. Yeah,
because it says removing a reaction.
I didn't say removing. I said addition.
Yeah, but for answer choice D, it says on the PowerPoint it says removing a reaction will result in it being produced. And for answer choice D, it says it results in it being produced. That's not addition.
No, it says products being produced on the question. Let me show you. Yeah, see. Look, see. So if you add, look, right? So it says, what will the addition of a reactant result in, right? It does result in more reactants being used, right? Because you've got to push it to make products, right?
I thought that said more produced.
Well,
I would like to add that I just read the first one and was like, yeah, that's right.
no, more products are being made. That is true too, right? And then also equilibrium is reestablished. So all that is true. Okay. Like I said, I'm gonna chalk it up to some of you guys still writing your pre-labs because that was a little bit disappointing. Okay, just a little bit.
Technically, I still got it right.
Okay, so next, change in temperature, right? Is the reaction endothermic or exothermic as written? That matters, right? In endothermic, heat acts like a reactant. Adding heat drives the reaction toward products. In an exothermic, heat acts like a product. Adding heat drives the reaction toward the reactants, right? Which I showed you a little picture of that before on the welcome chart. So just remember that, okay? And so let's take a look at what's happening here, okay? Let's look at what's happening. So here I have an endothermic reaction, right? Here I have an endothermic reaction. You know it's an endothermic reaction because I have delta H there, right? And it's greater than 0, right? That means it's not negative. That means it's endothermic, right? And so here in this reaction, we got heat plus some cobalt and some chloride, and we make cobalto chloride. Interesting. And it's pink. It starts out pink, and it becomes blue, right? And then you have some extra waters left over right there, right? So the solution appears pink because lowering the temperature shifts the equilibrium to the formation of the pink, right? Which is the reactants. But if you add heat, right, it actually shifts the reaction towards the products, and that's why you get more blue. See, so you can see based on just color there that for an endothermic reaction, right, when you add the endothermic reaction and you make heat to it, the heat makes it go towards the products, and cooling it down makes it go back towards the reactants. And you can see it in color. It's so neat. Man, that'd be a cool experiment to do in front of kids, right? Like, like because what you could really do is like if you were in a cold room and you had that, just having the cobalto chloride, it'd be blue, right? But then you just cover it with your hands to warm it up. It'll turn pink, right? And it'll be pink for a little bit, and then you let go again, and it'll turn back to blue again because of the coldness of the room. That'd be that's or mood rings and mood things. You know what I'm talking about? Huh? I, I'm sorry, I can't hear you because I have like a headphone in one ear. And say that one more time. Oh no, it's not off your mood. It's totally off your temperature. so, so, so really, so number one, so I don't even notice, but like those mood rings. Yeah, and I don't know if you noticed too, like those mood things are always black in cold rooms. They're always black, and then you put your finger on it, then it turns slightly more blue, right? But if you're like in the sunlight, it's already kind of blue colored, or even a little bit more. You didn't know that? Are you people serious? Oh my god! Are you serious? Well, but so I guess let me rephrase. It is a little bit based on your mood because you tend to get more hot when you're stressed, right? Like your skin gets hotter when you're stressed. Yeah, like when you're relaxed, you're actually feeling kind of cool. That's why when you sleep better when it's cold at night.
Oh my gosh, we literally were talking about this in my sociology class right before this. We were talking about how they keep jails really cold because they want them to sleep.
Yeah.
If you kept them hot, a lot of fights would break out.
Exactly, because
That's crazy that
heat,
we were
yeah,
talking about.
heat causes stress, and that's why if you're particularly stressed out, you're going to make the little heat mood thing a little hotter, right? A little bit more yellowish, orangish, right? But if you're relaxed, right, then your skin's actually a little bit cooler, a tiny bit, just a tiny bit, right? But that's the reason why sleeping in the cold is better. That's why they say to keep your temperature in your house at like 68 to get a good night's sleep,
Only
right?
68?
I think it's 68.
Like even at like 65.
Any colder than that, you might get frostbite. You know, any.
I get really hot at night though. I'm just like a naturally like
Oh no,
very
I
hot
understand.
person.
I understand that because I have a purple mattress because I get so hot at night that I have a purple mattress, and the purple mattress is like all these honeycombs that have no springs, and there's no cloth around it. It's all like, and it's super comfortable. I love my purple mattress. It was like $4,000, but you know you invest in your sleep. Sleeping is yeah. No, I mean like, but they last forever. They last forever, right? But okay, so back to this thing though. Yes, the color changes. It is definitely based on temperature, not your actual mood. But in general, yes, when you get stressed out, you do warm up a little bit. That's why the phrase getting hot. You know, like when you get angry, you're hot, right? That's where that comes from, right? But then on the other hand, right, if you're nice, cool, and collected, you're cool and collected. That's where that phrase comes from, right? When you're relaxed. Well, they used to give them around like during finals time when I was in school to see if you were stressed about finals, like the rings, even rulers that had them on there too. So yeah, if you're always, but the thing is, a lot of people will always be in like a cold room, and so their skin is the same temperature as the room, and when they use the mood thing, it's always going to be like blue colored. You're always cool, right? No matter how stressed you are, right? So it's kind of funny that way. It's kind of funny that way. What stencils? Does that have to do with mood rings too? Or is that completely tangential? Oh, I know how. I know what it is. It has to do with chemistry. It has to do with chemistry. I got you. I got you. So let's talk about then an exothermic reaction, right? If you remember the Haber process in producing ammonia, that's an exothermic process. In fact, many of the reactions we talk about are exothermic, right? They cause some kind of explosion, some kind of heat or light's radiated, right? So most of them are exothermic. One would think that cooling down the reactants would result in more product. However, the activation energy for this reaction is high, right? So this is the one instance where the system in equilibrium is affected by catalyst, right? Oh, my thing just showed up. Oh, there it goes, right? So for an exothermic equilibrium, just remember that it is the opposite of what an endothermic one is, right? Okay, does that make sense? Okay, just remember that. So let's just talk about catalysts real quick. We've already talked about catalysts so many times before, but we'll talk about it just a little bit more. Catalysts increase the rate of reaction of the forward and the reverse reactions. Equilibrium is achieved faster, but the equilibrium composition has remained unaltered, which you know that already, right? The activation energy is lowered, allowing the equilibrium to be reestablished at lower temperatures. So here we have our reaction energy diagram, right? And we have the energy on the y-axis, the reaction pathway on the x-axis. Of course, the reactant is A here, the product is B. So what happens is, a reactant has to go up to this transition state and then come back down to B, which is always lower than A for a reaction to occur. But for a catalyst to be there, if a catalyst is there, it turns this really high activation energy right here to something just a slightly bit lower, and so it makes it happen a little bit faster. It happens a little bit faster. So what you can do there is that since you have a catalyst, you can actually be at cooler temperatures and the reaction will work better, right? Whereas on the other side, with the endothermic reaction, it was backwards, right? So this is quite apparent in your body, for example. Many of the reactions that happen in your metabolism, right, in glycolysis, the TCA cycle, the electron transport chain, right, fatty acid metabolism, many of those reactions would not be possible inside your body at the temperature it is. I know it feels like it's pretty hot at 98.6 Fahrenheit, right? But many of those reactions actually take way higher temperatures, right? But since you have enzymes in your body that act as catalysts, it brings down the activation energy so those reactions actually occur in your body at that temperature, and you're alive still, right? You're alive.
Some people say that eating spicier foods increases your metabolism.
I think that I have heard that, and I think that is semi-true, but it also has to do with the chemicals that are in spicy food too, right? Not that they're catalysts, but that I guess they could be catalysts, but the problem with it is that they don't come back as normal. Like, for example, one thing in spicy food is called, what is it called? What's the active ingredient in spicy food? I knew what it was a second ago. You just had to ask, and I didn't remember it. Dang it, what is it called? Oh my God, I can't remember. Anyway, whatever that is. I know for a fact it gets decomposed in your body, right? But that same thing, though, right, might actually help your. But I mean, is it really helping your metabolism because it's speeding up a reaction, or is it making it so that it's like your body is hotter? Does that make sense? Because a lot of people start sweating when they eat spicy food, right? And they start turning red, right? And then if you put yourself on a mood ring or a mood thing, it turns red after you eat like hot wings and stuff like that. So, but see, the problem with that theory though is that even though you feel like you're hotter, your temperature inside your body is still 98.6 degrees Fahrenheit. It will always be that way unless you have a fever or you're hypothermic, right? And so it can't be, that molecule can't be raising the temperature of your body to make your metabolism faster. So I guess it's one of those things where it is a catalyst, and you'll learn more about this later on in life, but there are such catalysts that will increase reaction rates, but you can't get them back, right? They don't come back to be normal again. And that happens a lot in biochemistry. But so maybe you're right. Maybe that is it. Like thinking it through that way, maybe that's where that comes from. But I think a lot of people also associate the fact that when you're eating spicy food, it takes more energy, and that's why you're like sweating and you're getting hot. And it's almost the same thing as when you're working out, you're sweating and you're getting hot. So maybe that's why people connect it to each other, right?
You're saying that if I just eat spices in a while, it'll be the same exercise.
I don't know, honestly. Maybe. I mean, maybe, you know. Dang, what is the spicy food ingredient? The thing. Oh my God, I can't remember. I remember that salt. It's fat soluble too. So if you're eating a bunch of spicy food, you need to drink milk to cool it down. No, what is it called? Hey Siri, what is in spicy food? Oh, there it is. Capsaicin. Yes. No, Siri. Don't you know Siri like learns you? Like Siri learns the way you talk, right? So you don't actually have to say any super specific thing. They'll know Siri will know exactly what you're asking just by the way you talk.
That's creepy.
Yeah.
So don't they have that supplement?
Yeah, absolutely. Yes.
In your Amazon cart, or it will show you your suggestions.
That's how it is anywhere. Like, and I'm like, the FBI watches you. And I'm like, you're watching
Siri
us.
watches.
Yes.
That's the thing.
And then it started showing me ads for like new mothers, and I was like, no.
Y'all need to watch this.
New mothers. Oh my God.
Have y'all seen the movie Snowden?
No, I haven't
Oh my
actually.
god, you'll have to watch it.
That's funny though.
It's crazy.
But yes,
It's a real guy.
I would. You know what? I'm just curious. I'm looking into that. What does capsaicin do to you? Because it does seem like it would make your metabolism faster. So, all right. So, this is your next question here. Which is not true about catalysts and equilibrium? Which is not true. Catalysts increase the rate of reaction for forward and reverse reactions. Equilibrium is achieved faster, and the equilibrium changes accordingly. Composition changes accordingly, or the activation energy allows the activation energy is lowered, allowing the equilibrium to be reestablished at lower temperatures. Right? Read these questions carefully and these answers carefully. All right, so this was, what is this one? Lecture 11. Lecture 11. Catalyst, there it is. 7 people have responded. Oh wow, wow! I'm very proud of you right now. I'm very proud of a lot of you. Not all of you, but I'm very proud of. I'm proud of most of you. Still waiting on 2 more reactions, or not? Okay, it's okay. It's okay. It is totally okay. It is totally fine. There should be. Was that you, Hannah, that just did it, or are you still signing in? Okay. It's okay. Okay, which of the following is not true about catalysts and equilibrium? A, catalysts increase the rate and of the forward and reverse reactions. Equilibrium is achieved faster and the equilibrium composition changes accordingly. Or activation energy is lowered, allowing the equilibrium to be established at lower temperatures. Or all of these are true. And let's see how we did. Oh my gosh, I'm so proud. Very proud. The vast majority of you there saw the little trickery I did in that question, right? The little trickery saw right through me, because the answer is, in fact, the not true thing is, in fact, B, because the equilibrium composition does not change accordingly. What does it do? It stays the same, right? No matter what you do to a reaction, there will always be the same equilibrium compositions, right? Remember that, okay? Good job, very good job.